Good afternoon. So this is a new technology that not many of you know about it. So it's a technology that took about 10 years to develop with funding from different funding agencies in the US. And so the idea is to come up with a manufacturing technology that's similar to conventional semiconductor manufacturing, but it's all liquid-based and it's all additive. So I'm going to introduce the topic and how it works. And then I'm going to show you some examples where we have applications in printing of metal, printing of dielectrics with examples, and then printing of active devices and logic gates. And so most of our stuff, with a few exceptions, is all inorganic ink. And so our ink sources, we buy from the same companies for some of the metal ink, same companies you actually all buy from. But for inks that are not available, we have to look for other sources that are not in this industry, but in other industries. But they have suspended particles in aqueous or other types of liquids. And then I'm going to show you how we can put all this technology together so to be fully automated, where you get to a point where you submit your CAD file and everything is done automatically. Basically, it's all hands off. So the idea was started about almost 15 years ago. I worked for 25 years in the CMOS semiconductor industry with IBM, Intel. So that was my background. And so about 10 to 15 years ago, we started thinking, well, is it possible to actually go from something like this? I don't know if this is working or not. Go from a big fab like that to actually a one machine like this. This is a machine in our lab, in NanoOPS lab. And so to have on-demand electronics in a wafer that has several layers of devices in 1 hour, no etching, no chemical reaction, all liquid-based, no vacuum, about 100 times less cost to produce the same thing, and it's about 10 times faster than, about 100 times faster than typical fabrication technique, and it's about 1,000 times faster than typical inkjet approach. And we have demonstrated the technology, as you will see, down to 25 nanometers. So actually it works down to the nanoscale, as long as your particles are small. So we worked with particles as small as 3 nanometers and 5 nanometers. And of course, if you replace the semiconductor industry, then you're saving all the etching steps and you're saving a lot of materials. So how is it different than inkjet? Well, with inkjet, as you know, you have a liquid and you have a droplet, and your resolution is limited by the size of your droplet, and you make dots to make a line, for example. And then also the alignment when the registration from layer to layer is limited by the mechanical stage that you're working with. So we avoid all of that. So basically our resolution is limited by the particle size. So if particle size is 10 or 20 nanometers, we can go down to that small. And also because we do use lithography, so our tools and equipment that are made by the company comes with lithography. So you don't have to worry about that. Everything is included. All you have to do is just load up your CAD file, your mask file. And basically we take the particles, we apply lithography to functionalize the surface, just like when you do electroplating, and basically drive the particles using either electrophoresis, electric field, or convective flow to the particles land exactly where you need them. So you make your pattern as you see there. So it's very fast. We can do a 4-inch wafer in 1 minute, even if you have submicron features and even if you have a very dense circuit pattern. This is one example I'm going to talk about. We have about 5 or 6 different, we call it directed assembly techniques, because we direct the particle to go where it's supposed to go. And so I'm going to talk about 2 techniques. The first one is electrophoretic, where we apply electric field, typically a DC field, but you can also apply AC depending on the zeta potential of the particle. And that is about 2 or 3 volts, mostly 2.5 to 2 volts. And so as you can see here, this is vias. These vias could be a few microns or could be submicron. And these vias, you apply about 2 volts. The particles are in the suspension. In a lot of these cases, this is aqueous suspension. This is gold.